In this project, you're going to get to explore the Wilcoxon rank sum test a little bit more. This project follows directly from a previous video on the Wilcoxon rank sum test, so I strongly recommend going through that video first, and then you can move on to this one. So what you want to do here is simulate the effects of the mean differences between the two populations, and also differences in standard deviation between the two populations on the resulting statistic of the Wilcoxon test. Now, when you do this once, it might not be very representative. So what you want to do is run a scientific experiment and repeat this statistical test 100 times, each iteration with the same mean difference, but different randomly generated numbers. The two data sets that you're going to generate are very similar to the two data sets you generated in the previous video. These are log normal distributions, so it's e to the mu1 times e to the, or you could even drop this e and say e to the mu1 plus r1 divided by 2. The main difference from this project and the previous project is here you want to vary mu1. So you can see mu2 should be fixed at 5, and mu1 should range from 5 to 6. And the random numbers R2 are drawn from a normal distribution with a mean of 0 and a variance of 1. And then the random numbers for R1 for distribution 1 are going to have a range of variances. So the mean is still going to be 0, but the variances should vary over different runs between 0.1 and 1. So these are the two parameters that you have to vary. And once you vary those two parameters, that's going to give you results, effect sizes from the Wilcoxon test over a two-dimensional parameter space. So the color here corresponds to the size of the effect, the size of the difference between this population and this population. And the idea of repeating the experiment 100 times is you want to generate this entire two-dimensional map 100 times, and then this resulting map that you see here is the average across all 100 of those iterations. And the bonus exercise is not only to just implement this project, but also to look at this result and think about what it means and try to make some statistical interpretations about the relationship between the difference in the means versus the differences in the standard deviations between two populations. Good, so good luck solving this project in MATLAB, and now I will switch to MATLAB and you can watch me solve it. Okay, so here we get to range over parameters. So if you're not really sure how to set this up here, I think it's useful to look ahead to the code and figure out what's going on. So here we have a loop over the mean differences, a loop over the standard deviations, and finally a loop over trials. This is what I called repetitions or different experiments. Here we're going to create the two data sets. So it looks like data set 2 is already created for us. Remember, that was a log normal distribution with a mu parameter of 5 and a variance of 1. So that's already implemented here. So now the question is, how should we set up this data set here, data 1, and what implications does that have for how we should define these parameters here? So I think we should say that this mean diff parameter should range from 0 to 1. And let's just say 40 steps. Now you might be thinking that this is wrong because the instructions clearly said that the mean of data 2 should go between 5 and 6, not between 0 and 1. However, what this variable indicates, and what we're going to end up plotting on the y-axis of that colorful graph, is the magnitude of the difference in the means between the two data sets. So you could actually put 5 and 6 here. There's nothing wrong with that. But what I think I'm going to do, I think it might be a little bit more instructive to have it be 5 here, and then I say plus mean diff, and then this is going to be the mean ith element. So, but there's several ways to solve problems in MATLAB. So if you prefer to set this up as 5 by 6, 5 to 6, and then get rid of this, that is also okay. All right, so now the standard deviation. This one is a little bit clearer. This is going to go lin space from 0.1 to 1, and I would like to have this in a different number of steps, so not 40, any number other than 40. I'll pick 60. And that's really just because when I create the plot, I don't want to have any confusion about which variable goes on the x-axis and which variable goes on the y-axis. Alright, and here we have 100 trials. So let's see, we need to initialize the results matrix. So that's going to be the length of mean diff by the length of std diff. Now, you could have also solved this problem by saying n trials, it's not with this comma here, and then you would put each of these results into its own separate trial. This would be a three-dimensional matrix, and then in the plotting you would average over the first dimension. So that also can be useful in some situations. However, in this case, I don't need to save the data from every single iteration, from every trial, so I don't need to save an extra dimension in this variable z results. Okay, this is good, so we're getting somewhere. Now I need to add the variance, so add some random data to this. So it's going to be plus random n comma 1, so that's the same thing here. I'm adding n random numbers. And now the idea is that these random numbers get scaled according to this standard diff variable. So times std diff. And now this is going to go over this stdi variation. Okay, so there's still a few things missing, but looking through this code, I can already see where this script is going to give me an error. Can you find it? So this script is going to give me an error on this line and also on this line because we haven't defined n. So n is the number of data points in each distribution, and we can use 40 because that's what we used in the previous video. Now we want to run the z-test. Now in the previous video we also saved the first output, which is the p-value. However, we don't actually need the p-value here. All we want is the z-value, which is contained inside the third output here. So that was rank sum and then the two distributions, so data 1 comma data 2. Okay, so I want to start running some of this stuff just to make sure that everything is good. So initialize these guys. We don't need this yet. Okay, so these two work, and now I would like to plot these two, see what they look like. Okay, so there's one of the data sets and the second data set. Now, of course, it's a lot of random numbers, so I don't really know what to think of it. But I want to confirm that there are indeed 40 numbers, and they're not NaNs or all zeros or anything else. So far, I think things are going well. Okay, so let's see what S is. And again, I don't really care about the actual values here. I mainly just want to make sure that this is giving me a valid output as a sanity check that I haven't made any mistakes yet. Now I want to collect the results. So now what we can do is say s.zval. Here's going to be some plotting. First we need to divide by n. This is a little bit tricky because here n refers to the total number of trials, not the total number of data points, which happens to be the variable called n. So let's say z results equals z results divided by n trials. So that's going to give us our average. I would like you to look through this code and see if you can find what is wrong with it. So what's wrong with this code is that every iteration I'm overwriting this variable. So that means I'm not actually running this, or I'm not actually storing the results over 100 iterations. It's only storing the most recent one. Okay, so the solution here is to say this matrix, z results, equals itself plus the new value. And then it makes more sense that we're dividing. So here we're summing up more and more data points, and here we're dividing by the total number of data points, and that's how we get the average. Now I would like to, let's see, generate this plot. So this is going to be, on the x-axis, will be the std diff, so the differences and standard deviations, and then it's going to be the mean diff, and then the main result is z results. So first of all, I wonder if this is the right order or if it goes the other order. And that is the reason why I wanted this to be a matrix with a different number of rows and columns. So let's try running this. It doesn't contain any interesting results yet. But at least it will crash or not crash, and it didn't crash. It gave me a warning, but that's just because Contour doesn't like drawing totally constant data. I think this is going to run now. The rest of this code looks fine. So let's run the entire cell by pressing Control Enter. So this takes quite a while, particularly this function can take quite a while. So I think I'll let this run and then I'll cut the video so you don't have to wait along with me. Okay, so that took a good 30 seconds or so. And here we see the result. So this is the z-score, and basically larger numbers, which corresponds here to redder colors, indicates a larger significant difference between the two populations, dataset 1 and dataset 2. So there's a few things that we can say about this. First, just purely aesthetically, it's pretty neat how the colors along here happen to line up perfectly, almost perfectly, with the color bar. That was not intentional, and that's not trivial, it just sort of happened to work out that way. But there is a more important statistical thing that we can determine from this. So one thing is that if the mean difference between the two populations is very small, it doesn't matter if the standard deviation, if the variance of one of the populations is big or small, there's basically not going to be a significant difference between the two populations. And on the flip side, when the mean difference is large, and you can imagine that this can go up, there's no reason why it has to stop at 1. When the mean difference is large, and the larger the mean difference gets, the less it matters how much variance is in one of the populations, because the z-score, the effect size, is going to be very large no matter what. And what's interesting is this period in the middle, this range here, where the mean difference is moderate, and here it really matters what is the standard deviation of one of the populations. So having a small standard deviation or a large standard deviation can mean the difference between having a statistically significant difference between the groups and not having a statistically significant difference between the groups.